So let us start with this. So in the previous uh, lecture, we have been talking about the interaction representation or the Dirac representation, and we have also seen the connection between the different representations, which are Heisenberg representation, Schrodinger representation, and the Dirac interaction picture representation. So we have seen that in the Heisenberg representation, operators are basically time dependent, and they evolve. They satisfy an equation of motion, which is known as the Heisenberg equation of motion, whereas state gates are basically time independent. In the Schrodinger representation, it is just the other way around, and the state gates evolve via the time dependent, and the operators are time independent, and therefore they have no evolution equation for we don't have any evolution equation for the operators. And in the interaction picture of the Dirac representation, both the operators and the state gates are time dependent, and therefore both of them have a dynamical evolution equation. And we have seen that the operators in the interaction representation, they evolve by the Heisenberg equation of motion. And the important thing is that the evolution is governed by the free part of the Hamiltonian, and therefore what we have is the following: I h bar del t that is equal to O hat I e. This where the Hamiltonian, the full Hamiltonian, is h naught plus p hat. So this is the interaction part, this is the free part, and this is the full interacting theory, full Hamiltonian of the interacting theory. And you can see that the dynamical evolution of the operators in the interaction representation is governed by the free part of the Hamiltonian. And we have also seen that the state gates in the interaction representation is their equation, dynamical evolution equation, is governed by, once again, their evolution equation is this, and where V hat I is the potential, the interaction in the interaction picture. That is, V hat IT is given by its dynamical evolution is basically governed by this equation. Okay. So this we have seen in the previous class, and in the previous discussion we have also introduced an evolution operator. You have T. We have introduced it this way. Evolution operator where U hat T is nothing but e to the power of and what is important is the following, that here we should remember that H hat naught does not commute with V hat. This is what is important. And the evolution operator is of this form. Okay? And we have seen that since psi ti satisfies this equation, therefore U hat t also satisfies a similar equation, that we can immediately find it out. So if we just substitute this thing here, then we shall immediately get that this is equal to V hat I t U hat t. So you can see that the evolution operator U hat t, which comes here, also satisfies an equation which is similar in structure to this, to the equation satisfied by the state gates in the interaction representation. And from here, on the definition of the evolution operator, you can immediately see that u hat t, u hat at time t is equal to 0 is identity. It's identity operator. Okay. What we shall do now is try to solve this differential equation. You can see already that this is a differential equation, but it is a little bit tricky because here it is a differential equation involving operators. So we should be careful about time orderings and things like that. Whenever there are two times, we should remember that v hat I, an operator defined at a time t1, in general do not commute with an operator defined at a later time, at a different time t2. Okay? So this is why this is a differential, since this is a differential equation involving operators, therefore we should be very careful while solving, while trying to find out a solution for the differential equation. So let us try to find out a formal solution to this differential equation. What we shall do is we can write this in the following form. U hat t is nothing but minus I by h bar v hat I u hat t del t. U hat t is this, and therefore if we just integrate, what we shall get is the following. We shall get minus I by h bar integral 0 to t v hat I t1 u hat t1 dt1 plus some constant of integration, which is also an operator, because this left hand side is an operator, right hand side is an operator, therefore the constant of integration must also be an operator. Okay? And we can immediately find out the value of this operator, the constant operator, by using this initial condition. Note that u hat at time t is equal to 0 is identity operator. So this thing at time t is equal to 0 is identity operator, and at time t is equal to 0, this integral is runs from 0 to 0. So this value of this integral is also 0, and therefore the constant c gets identified, can be identified to be the identity operator. And you can see that this is a formal solution to this differential equation, but it is not really a solution, because you can see that our unknown here was in the differential equation, the unknown is this operator u hat t. What we have done is we have converted the differential equation to an integral equation, because now the unknown, see, this is still the unknown, so you cannot say that this is a solution to this differential equation. What we have done is converted this to an integral equation, because the unknown here, which is the operator u hat, it appears under an integral sign, and therefore it is an integral equation. But once again, this is a tricky kind of an integral equation than the standard one that we encountered in mathematical physics course. This is an integral equation involving operators. What we usually learn in the mathematical methods course are integral equations where everything that appeared here in the equation are functions. But this is an integral equation involving operators. So this is what we get. Now, from here, what we shall do is the following. You can see that this is the unknown that appears here. So we can immediately write, by changing t to t1, we can write u hat at t1 is identity operator minus I by h bar integral 0 to t1 v hat I t2 u hat t2 dt. See, this relation is also exact. Formally, you can write this, and we have not done any approximation so far. So this is also exact. Now what we shall do is, we shall substitute this here. because this is u hat t1 and we have an expression for u hat t1. So we shall substitute it there, and then we shall get u hat t is equal to, I hope you can see the board. What we shall get is identity minus I by h bar integral 0 to t v hat I t1 identity minus 0 t1 t2 and then so what we have done is we have substituted u hat t1 here and we have obtained this expression. This expression, so you can just simplify this further. What we shall get is this we had I t1 t1 is the first term, and then we get minus I whole square integral 0 to t we had I t1 dt1 then integral 0 to t1 we had I t2 you had t2 Is this clear? Is it okay? Can you see the board?
Yes, sir.
Okay. So you can see that we have obtained a formal expression for u hat t. We are trying to develop a series expansion for u hat t. And so up till this part also everything is exact. It is still an integral equations because this part is known. You can if you know the form of the interaction, which is known actually, therefore you can evaluate it in the interaction picture. You can find what v hat I t1 is. You can integrate this and you can obtain an expression for it. But for the second order term, for the second term, or rather the third term, you can see that you had t2. So the unknown again appears under the integral sign, and therefore you cannot obtain an expression for this term. So you can keep on continuing this. You can keep on doing this thing. So now what you can do is you can find out the expression for u hat t2, and you can put it there. From the expression that we wrote down at the beginning, you can find out what u hat t2 is, substitute it here, and you can get the second order term, and so on. Again, u hat t2, u hat t3 will appear under the integral sign, and therefore it will still be exact, but you will not be able to know the last term. You will not. So you will not be able to know what exactly this u hat t is. But if you assume that the interaction piece that you have is small compared to the free part of the Hamiltonian, if you assume that, then you can actually truncate the series at some point. So you can treat this as a perturbative expansion. So you assume that each term in this expansion is smaller than the preceding term, than the previous term. So if you assume that, then you can actually get a perturbative expansion, a series expansion. And basically what you can do, now you can see that if you want to keep up to this term, up to just the second order term in the perturbation, then what you can do is just substitute. See, second order in the perturbation, by second order in perturbation, what I mean is that you keep two terms involving V. First order in perturbation, I mean, if you treat V as a perturbation, right? Your V is the perturbation. So by first order in perturbation, I mean this, the term involving only a single V. By second order in perturbation, I mean that the term involving two V's, third order and so on. So term involving three V's and so on. So if you want to truncate your series at second order in perturbation, so you just keep only this term. And then the thing is simple, because since you want to truncate to second order in perturbation, you don't need to get the term involving three V's. So what you can do is, you can just substitute, in place of U hat T2, you can just substitute the identity operator. That will give you the result for the evolution operator U hat T up to second order in perturbation. So what we will get ultimately is U hat T is equal to identity operator minus I by H bar integral 0 to T V hat I T1 dt1 plus minus I by H bar whole square integral 0 to T V hat I T1 dt1 0 to T1 V hat I T2 dt2 plus dot. So this term, the next term after this term is a term involving the product of three V operators, three V's, okay, and so on. So it is at this point we have made an approximation. If you want to keep up to second order in perturbation, then throw away these terms, and therefore you treat this series as a perturbative series. And it is at this point that you get an approximate expression for the evolution operator up to second order in perturbation, keeping terms up to second order in V. So at this point we have made an approximation, and this is an infinite series. And you may ask about the convergence of this series. So we assume that since this is a perturbative series, therefore we assume that it will converge. This infinite, we assume, it is just our assumption that this series, infinite series involving this perturbation terms, V's, will converge ultimately. But we are not here. We shall not look into convergence issues of this series. What we shall say is that we shall just treat this perturbative expansion for the evolution operator in a very formal way, and we shall try to use this perturbative expansion in calculations in calculating physical quantities, for example, transition rates, cross sections, lifetimes of decay processes. We shall use this thing there. When we try to solve a differential equation by converting it into integral equation, in the ordinary case, in the standard case which we learn in mathematical methods course, there everything, as I said before, that there everything are functions. Whatever appears, the unknown quantity, that is also a function, and whatever you have, those are functions. And in that case, such a kind of a perturbative expansion for the unknown function is usually said to be the Neumann-Liouville expansion. It is the Neumann-Liouville expansion. But as I said that this is an integral equation or a differential equation involving operators, this is the corresponding analog of or the counterpart of the Neumann-Liouville expansion, and this is said to be the Feynman-Dyson series expansion, or Dyson-Feynman series. So let's see what we can do further with this quantity. You can basically write this quantity in the following way. If we assume that this series will converge ultimately, this infinite series will converge ultimately. So if we assume that, and when we assume that the infinite series converges ultimately, then what we actually mean is that each of the terms that you get in the infinite series is smaller than the preceding term. And ultimately it will give you, if you sum all the terms, all the infinite number of terms in that expansion, you will get a convergent, you will get a finite answer. That is what we assume. But as I said that, let us treat this solution as a formal solution and see how we can apply this solution when we calculate physical quantities, for example, cross sections or lifetimes or and several other quantities that we can calculate from here. So this thing we can write it in the following way: is summation n is equal to 0 to infinity minus I by h bar whole to the power of n integral 0 to t dt1 we had I t1. So just here, so we get this, then we have 0 to t1, we had I t2, so on, 0 to tn minus 1, we had this is the dt2 here, we had I tn. So you can see that you can basically write this thing in a closed form this way. But the summation runs from n is equal to 0 to infinity, so the n is equal to 0 term gives you the identity operator, n is equal to 1 term gives you this term, n is equal to 2 gives this thing, and so on. Is this okay? Do you have any questions at this point?
Sir, the summation you wrote, it will only work if 0 to 2 dti v at I t1 dt1 to the power n. In this form, this summation will work. But
Just repeat your question once more.
I am saying that the summation that you have written in the wrote in the compact form,
Yes.
that form will work if I write the after minus I by h bar to the power n, then 0 to t dt1 vi cap t vi hat t1 to the power n. I mean whole to bracket to the power n. But this form doesn't mean the summation.
No, it actually gives you this term. You check it for n is equal to 0, what term you get from this closed form? For what is the n is equal to 0 term?
I don't know, because the multiplication are defined as various integrals. I mean 0 to t, 0 to t1, 0 to t2.
Equal to 0, what is the value of this?
That is 0 to t minus 1.
0 to t minus 1, but there is no t minus 1. So that term basically means that this is an identity. Okay. So everything over here, there are no integrals because there is no t minus 1.
Okay. Okay, sir. Yeah, I understood.
You understood?
Yes, sir. Yes, sir. Yeah.
So t minus 1 is not there, so no integrals are there. So you have identity operator. For n is equal to 1, you get minus I by h bar, this one. Where does it stop? What is this?
Minus, this is 0.
Is 0. If suffix 0, you call it to be t.
Okay.
Identity with t. So if this is t, then what is this? T1. So we have type t1 dt1, which is this term.
Okay.
But n is equal to 2, it is this. Then 0 to t dt1. And then what is this value? Where does it end? It ends at t1.
Okay.
That is t1 dt2 we at it2. This one. That is this term. And so on.
Okay, sir.
Okay.
Okay, sir. Yeah.
So when you write this in a compact form, you have to just remember that by your notation, t of 0 means t, and t of minus 1, 0 to integral 0 to t minus 1 actually means that there are no integrals. It is just 1. So that will identify this expression with this thing. It is just basically a formal way of writing this perturbative expansion. And on top of that, you assume the fact that this perturbative expansion makes sense completely. Makes complete sense in terms of convergence and other issues. Although it is very difficult to show the convergence of this series expansion. Maybe it will not. It may turn out that this series expansion does not converge at all. So you may say, why are you doing this? So it is not meaningful. But the only check is that when you calculate things by using this quantity, you try to calculate cross sections and lifetimes of decay processes. If it matches with the experiment, then you say that okay, your theory is fine. The only check is you have to match whatever you calculate from your formalism. It should match with the experiments. Okay. Now let us look at the second order term. See, you will notice one thing, that these are operators defined at two different times. So in general, as I said, they will not commute. Not only that, this integral runs from 0 to t, and this integral runs from 0 to t1, and then 0 to t2, and so on. What we would like is, we would like to convert all the integrals to run from 0 to t. That is what we would like to make or get. So let us look at the second order term. So what will be the second order term? Okay, let us do it in a different way. Let us construct a quantity like this. Let us consider this quantity. So now you see that we have brought in the time or ordered operator. Here, if you note that T2 is actually always lesser than or equal to T1, because T2 runs from 0 to T1. That is the maximum limit. And then T1 runs from again 0 to T. So you see that the maximum range of T2 is T1. So that is the maximum value that T2 can take. Okay. So now let us consider this particular quantity, where you now see that all the integrals run from 0 to t. And this is a time ordering of the product of two operators defined at two different times. Now this you can write it down as 1 by 2 factorial integral 0 to t dt1 0 to t dt2. And then you can write down the definition of this time ordering operator. This is basically a theta function, t1 minus t2. So this means that this will contribute only when t1 is greater than t2. When t1 is greater than t2, it is basically 1. So we shall have this plus theta t2 minus t1 d hat I where this theta function, we define it in the following way. Theta x is 1 when x is greater than 0, it is 0 when x is less than 0, and it is equal to half when x is equal to 0. This is quite important, because you see that by definition this time ordering operator, time ordering of this product of two operators is basically this, right? So when T1 is greater than T2, this thing is 1, this thing is 0. Therefore, you should get what is expected. D hat I T1, D hat I T2, because the operator defined at a later time should appear on the left hand side of this operator. And similarly, when T2 is greater than T1, this will be 0, this will contribute, and we have the standard thing. But what happens when T1 is equal to T2? When T1 is equal to T2, then both these times are actually the same, right? And therefore, it doesn't matter where you write down the two operators, because the two operators, they are same operators defined at the same time. Therefore, they commute with each other. Therefore, it doesn't matter where you write it down when T1 is equal to T2. So what you do is you just define it such that when T1 is equal to T2, it is half. So this will be half. So this will be here like T1 T2, but T1 is equal to T2, and this is also half. So it is same. So half plus half gives you V hat T1, V hat T2 with the condition that T1 is equal to T2. That is why you define the theta function with a half here for x is equal to 0. Because there will be overcounting, and therefore you just define it with a half. So that half plus half, you will get 1. So now, what we see from this thing is the following. Let us consider the first term. So this is basically equal to 1 by 2 factorial. The first term is an integral 0 to t dt1, integral 0 to t dt2, theta t1 minus t2, v hat I t1, v hat I. I will write down the second term, plus second term is again 1 by 2 factorial. Integral 0 to t dt1, integral 0 to t1 dt2, theta of t2 minus t1, v hat I t2, v hat I. So I have done nothing. I have basically broken this up into two terms. Now you see that, let us consider the first term. This thing contributes when T1 is greater than T2, right? Okay. So what we can do is, you can just change the limit of this thing. You can remove this theta function at the cost of changing T to T1. Is this okay? Right? So previously it was from 0 to t and you had a theta function. But this, you can write it, this expression, you can write it from 0 to t1 plus t1 to t2. Right? But so this integral, I am talking about this integral. You can write this integral as integral 0 to t1, then you have a theta function, and so on, and then again from t1 to t2, and once again theta function, and this integral is dt2 over dt2, and you have this all this operator stuff here. From this, if you look at this expression, you can see that here t2 is actually greater than t1. So this is t. This is t, not t2. In this expression, you can see that t2 is greater than t1, and t2 greater than t1 means the theta function will be 0, right? So this term will not be there, and therefore you will have only t2 running from 0 to t1. So in this range, t2 is basically smaller than t1, and therefore in that range the theta function is 1, and you just have the operator stuff with the range being 0 to t1. Is this clear?
Yes,
Yes, sir.
Good. Similarly, if you look at this term, here also you can play a trick. what you can do is let us look at this term now. So the first term is this, the second term will become 0 to t1, equal to 0 to this. Okay, this is not t. This is not t1, this is 0 to t. So it's a mistake. It's the second term. All the integrals are from 0 to t. So what you can do here is, since both the integrals are from 0 to t, so you can change the order of integration. That you can always do. So it was basically dt1, dt2. Now you write it as dt2, dt1. It's the same thing. And now here you can see that t1, it runs from 0 to t, but once again you can change this integral from 0 to t2 and t2 to t. In the range t2 to t, t1 is always greater than t2. Therefore, that part is again 0, right? So the only term that will come in this range from 0 to t2, t1 is less than t2, and therefore this theta function is 1. So this is 1. So this is basically this. It is just the argument goes similar. It is just similar to the first term. Now what you do is, in this expression, you can just see t1 and t2. These are all dummy indices, right? So these are integration variables. So you can just change t1 to t2. Then you can change t1 to t2 and t2 to t1. So if you do that change, because these are dummies, so t1 will get replaced by t2, and t2 will get replaced by t1. Similarly here, t2 gets replaced by t1, and t2 and t1 gets replaced by t2 by just making this transformation. Because these are all dummies. The variables t1 and t2 are integration variables. Therefore, you can just change them. You can call t1 as t2 and call t2 as t1. Nothing will change. Now you can see that something interesting has happened. This term is from 0 to t dt1, 0 to t1 dt2. We had a t1, we had a t2, and you can see that this term is basically the same as this term. And you see that, just compare the two terms, and you'll see that both of them are actually the same terms. Therefore, they will add up, and if you add it up, the final result will be this. The 1 by 2 goes away, 2 factorial goes away, and therefore you get integral 0 to t dt1, integral 0 to t1 dt2. This product of these two operators is basically nothing but this thing. Therefore, this thing you can basically write it down as 1 by 2 factorial integral 0 to t dt1, integral 0 to t dt2, time order product of b hat I e1, b hat I. And you can see that we have achieved our goal. What we wanted to do is, we wanted to convert the integrals running from 0 to t1, 0 to t2, and so on, to integrals, all of which run from 0 to t. But we have managed to convert everything, all the integrals running from 0 to t, but at the cost of introducing a time ordering operator. A time ordering operator which basically orders the product of various operators defined at different times. So you can similarly show that the third order term, that is the term involving the product of 3 v's, is nothing but the 1 by 3 factorial. You have to put a 1 by 3 factorial in front, and then once again it will be 0 to t dt1, 0 to t dt2, 0 to t dt3, time order product of 3 operators. So we have converted this at the cost of a time ordering operator and a factor of a factorial factor. a factorial of a number. So if it is the product of two operators, then you put a factorial 2. If it is the product of three operators, you put a factorial of 3. And if it's the product of n operators, then you put a factorial of n. So ultimately what we shall get is the following. You remember the series expansion that we derived, that we just now derived a few, maybe 20 minutes back. You had we had the summation n is equal to 0 to infinity and product of integrals. Now you can basically write it down as identity operator plus summation n is equal to 1 to infinity 1 by n factorial minus I by h bar equal to the power of n integral 0 to t dt1 integral 0 to t dt2 and so on, integral 0 to t dtn time order product of v hat I e1 v hat I e2 v hat I. So you can see that we have a nice expression, infinite series expansion for this evolution operator. It is basically this, and you can formally write this down as time order product of e to the power of minus I by h bar integral 0 to t v hat I t1. So this full infinite series expansion, you can write it down in a closed form as time order product of e to the power of minus I by h bar integral 0 to t v hat I t1 dt1. So this time order product of this exponential thing basically is equal to this thing. So this is a formal expression for the evolution operator u hat t, the perturbative series expansion, infinite series expansion, and with this is it is a very important tool in calculating various physical quantities, as we shall see in our later discussions. So do you have any questions at this point? You can try and check for the third order term. You just start from 1 by 3 factorial and write it down. Write down the definition of product of time order product of three operators. You write it down and then you try to expand this, and you shall get the required thing that you want to show. Is this clear?
Yes, sir.
Yes, sir.
Do you have any questions? Do you have any questions? So as I mentioned just now, that you can try to show that indeed the third order term you can write it down in this way. So you start from here, put a 1 by 3 factorial time order product of three operators, and try to show that it is indeed equal to the third order term in the expansion that I wrote at the beginning of this class, where the integrals do not run from 0 to t. It runs from 0 to t, 0 to t1, 0 to t2, and so on. So if you don't have any questions at this point, then let us stop here for today.
Sir?
Please.
Is this called Feynman-Dyson expansion?
Exactly. This is the Feynman-Dyson this is the Dyson, or rather you should call it as the Dyson-Feynman series expansion, or Dyson expansion, and also call it as the Dyson expansion. This is the Dyson series expansion. This is basically the analog of the Neumann-Liouville expansion that we encounter in ordinary integral equations. By ordinary, I mean that integral equations which involve functions only. So it is the operator analog of that. And since you are dealing with operators, therefore, as I said, that you get this time ordering, you need to order the operators in the appropriate way, because operators, same operators at different times do not commute, and therefore you get the time ordering operator. This is the Dyson expansion. And ultimately, from this Dyson expansion, what we shall see in the next class, it will actually give you the S matrix. What is known as the S matrix in the literature.
The exponential form that you have written in the last slide, this is not an exact value, right? Because we are neglecting the mu that is reappearing again and again.
We are neglecting what?
The mu cap term, mu hat t.
U hat term. Yeah. See, this is an infinite series expansion. This runs from 1 to infinity. It's an infinite series. So it goes on and on. And therefore, you can write it down in here. We have not neglected anything. We have only assumed that this infinite series expansion will actually, this is a formal solution to the integral equation or the differential equation. It's a formal solution. We have only assumed that, okay, this series expansion will make sense. By making sense, I mean that it will converge. It will give you a convergent value. Now, what do you mean by convergence of operators? That is a different issue altogether. But once you write it down, this is an infinite series, and you write it down in a time-ordered product of an exponential. This you have just nothing. We have derived it, and we write this in this form. If you expand an exponential, e to the power of x. E to the power of x is an infinite series, right?
Yes.
So that is what it is. Okay. So let us stop here for today.